Let's talk about what's going to go on in a line integral. Then we'll write some notation for the line integral, see how it relates to the notation that we always use for integration, and then get into some calculations. And then the rest of the week, we're just going to be practicing calculations with line integrals. We want to practice calculations with line integrals. All right, so with line integrals, we're really going to be looking at the effect of the vector field on some path through the vector field. We're going to focus on this second question. What is the effect of a vector field on some path through the vector field? This is where we're going to look at the interaction between two vectors. So here, the effect of the vector field on a path through the vector field. Here we're going to be concerned about the interaction between two vectors. I'm also going to use my highly technical phrasing. We're going to be doing this at a bunch of points because that's what integration is about. We're about doing some calculation at a bunch of points. The integral from a to b of f of x to x is we're evaluating f of x dx at all the points from a to b. We're just doing something at a bunch of points. That's what integration is about. Here we're going to be looking at the interaction between vectors from the vector field and vectors from the path. So we're going to have vectors from the vector field and vectors from the path. The two vectors are going to be vectors from the vector field and vectors from the path. Those are the two vectors that we're going to be looking at how they interact. Vectors from the vector field and vectors from the path. So vectors from the vector field at a point, that's pretty clear. The vector field is defining a bunch of vectors. But what do we mean by vectors from the path? The path is a one-dimensional curve through two or three-dimensional space. And if you had guessed that we are going to look at the tangent along the path, then you are correct. That's where we're going to get vectors from the path. So these are vectors that are tangent to the path. So there's going to be the path, and we're going to look at each point along the path, we're going to look at a vector tangent to the path and see how that interacts with a vector from the vector field. So for a picture, if we've got some vector field, which is just a bunch of vectors, I'm going to use the same foreign vector field that we had yesterday. And then we've got some path. So here's our vector field, a little piece of a vector field, kind of a boring vector field. I couldn't think of a spooky vector field, so for Halloween. So mainly because I couldn't define spooky in terms of vector field. So here's a vector field, and then there's going to be some path running through the vector field. So now the path is just going to be a one-dimensional curve. I don't know why my path had to be so curvy, but but I wanted to hit one of the tails of these vectors. And the two vectors, so the curve itself is just a bunch of points with some orientation running through the vector field. And we're interested at a particular point, the interaction between the vector field and a vector tangent to the curve, the direction of the vector field. So it's kind of coming across this way with some kind of magnitude. So there's the vector field at some point, and there's the direction of the curve, a tangent to the curve at some point. So this green vector here is just the vector field evaluated at some point x naught, y naught. The curve, we're going to have to do a little bit more work to describe. Remember, we described curves in R2 and R3. We can describe a one-dimensional curve in R3 or even R2 by parameterizing the curve. So we're going to take curve C and we're going to parameterize it with some vector. So curve C is going to be parameterized by R of t. And at each point on this curve in the vector field, we care about what's going on, what the direction of that vector is. So we care about the direction of this vector. So this vector is going to be R prime at some t naught. This is the core operation in the game. I've got the vector field at a point. I've got a tangent to a curve at a point. I want to know how they interact. You know we're doing integration, so you know there's going to be multiplication. Since we're dealing with vectors, I want the dot product of those two vectors. I'm going to want to know what f is doing at the point x naught, y naught. Now, at the point x naught, y naught, that's some value of t. So this is going to be f evaluated at the location given by the parameterization. So here is r of t naught. So there's the vector field evaluated at that point. And we're going to multiply this by the derivative. The direction of the vector. Oops. I left off the important part of the multiplication. Because I'm multiplying vectors, so I have to specify what kind of multiplication I want. So what is this going to tell us? What is this dot product going to tell us? It's going to tell us what the dot product always tells us. How much of this vector is going in the direction of the curve, or how much is the direction of the curve going in the direction of the vector field. Usually I think of this as the effect of the vector field on the path. So how much of the vector field is going in the direction of the curve? That's what we want to know. How much of the vector field is going in the direction of the curve? Is this vector field pushing with the curve or pushing against the curve? realized I used blue for the path and green for the vector field, and I want to plug the parameterization into the vector field, so now I got the blue and green together. Probably have to switch one of those up. Any questions? At the core of a line integral is the interaction between the vector field and the curve. The way we get a vector from the curve is to just grab a vector tangent to the curve. Now you can see our vector field here is constant, but our curve, the direction on the curve is changing continuously. And we could also imagine this with a continuously variable vector field. That's going to cause us to want to integrate. So here's what we're going to do. We're going to do the same thing that we always do with integration. If this vector field was constant and this curve was constant, then all I'd have to do is calculate the dot product. And life would be easy. But we need to prepare ourselves for a situation where one or more of our factors is continuously variable. So we're going to think about this the same way we think about everything. We're going to pretend that things are constant for small changes in the path along the curve. So when the path is continuously variable, we do the integration thing, trademark. I'm just kidding. You can't trademark the integration thing. But that's what I'm going to call it in my book. It's the integration thing. We're going to make things constant and add. We're going to assume that things are constant for short changes in our parameter. We're going to assume the vector field and the path are constant for some small change in the parameter. Multiply for the multiply, which is calculate with the dot product. And then add up all the results. Just like we always do. Want to use multiplication? Things are continuously variable. Make things constant for some small changes so that we can multiply, and then just add up the results. Then to improve our approximation, we use more small changes in the parameter. This is the line integral version of smaller rectangles or more rectangles that are not as wide, smaller value of delta x. And then the calculus thinking. What happens when we use an infinite number of small changes in the parameter? So we take that curve, and instead of thinking that continuously flowing curve, we imagine the curve to just be a bunch of line segments, a bunch of tangents. So the curve, instead of being this continuously flowing curve, it's just a tangent here. And then a little later, we use a tangent. And then here we use a tangent. And then here we use this tangent. And it's just these tangents. Not really line segments. At each point, we're just drawing the direction vector. That's kind of the weird thing that's going on here. I'm not imagining the curve as a bunch of line segments from one point to the next. I'm imagining the curve as a bunch of tangents. We're imagining the curve as a bunch of tangents, not a line connecting one point to the next. This is most closely related to calculating the arc length way back in Calc 1 or Calc 2, way back in single variable calculus. This is most closely related to arc length. It's a bunch of tangents, not line segments connecting the points. So the curve is a bunch of tangents. So think of the curve as a bunch of tangents, not as line segments. So see, like an arc length. So it's a bunch of tangents, like we calculated arc length. Let's see what our notation is going to look like. This is the thinking behind a line integral. We're imagining the curve as a bunch of tangents. At each of those tangents, we figure out what's going on with the vector field. We say, what's the vector field doing and which direction is our curve going? And then we just use more tangents. We just use more tangents. And then calculus style, we just use an infinite number of tangents. Any questions on the thinking? Because if there are, I don't know if I want to answer them today. I'm just kidding. Are there any questions on the thinking? I just wanted to show off my lightsaber. That's why you're all staying away, because you don't think I can force choke you through Zoom. If you keep your camera off, I can't. So it's like 5th edition. It's all like target that you can see. Ugh, such a pain in the butt. Also, sleeves are bullshit. It's ridiculous. This is why I don't wear sleeves, because they like catch on stuff. I keep like not, I have to be like all careful. Anyway, what are we talking about? Oh yeah. It stresses me out when my wife washes dishes, because if she has long sleeves, she doesn't roll them up. It's crazy. How do you not ruin your shirts if you don't roll up your sleeves when you're doing the dishes? That's beside the point. Beside the point. Let's talk about line integrals. Specifically the notation. I want to take a minute to talk about line integral notation, because this does tell us something about what we are doing. So we want to integrate a vector field over some path. We're going to integrate a vector field over some path C. We're going to parameterize C with R. C is going to be parameterized by R for T from A to B. These are the parts that we need. The generic line integral notation, it's bugging me that this is in the box, is, say, the integral over C of f dot dr. Dr is going to be a small piece of the curve, a small tangent to the curve. That's what that dr is. That's that small tangent to the curve. So what will we, this is generic notation, and it's an integral, and it tells us exactly what we're doing. We're going to take f dot dr and evaluate that at all the points along the curve C. Evaluate f dot dr at all the points along C. That's what this notation tells us. I didn't have to talk about line integrals at all. This is what integral notation means. We're going to evaluate f dot dr at all the points on C. In C, on C, doesn't matter. Because that's what integral notation does. We put the integral over C says, this is what you're plugging in to the expression. F dot dr is the expression. This doesn't tell us how to do this. It just tells us what we're going to do. Let's talk about how we're going to do this. C is parameterized by R of T. So at all these points, I'm going to need the vector field. The vector field that we're integrating, I'm going to need to evaluate this at the parameterization at all these points. So here we are evaluating the vector field at all the points on the curve. That's what that part of the expression means. This is the vector from the vector field at all the points on the curve. That's the vector from the vector field at all the points on the curve C. We find the dot product with a tangent to the curve. So the parameterization is r of t. The tangent is going to be r prime of t dt. Remember, we're imagining the curve as just a bunch of tangents, not line segments, tangents. And we're doing this for all the points along the curve. So we're going to integrate. Now we have an integral. The expression is all in terms of t. So we're just going to evaluate this at all the places, at all the values of t. And t is the parameterization of the path from A to B. Notation tells us a lot. Our knowledge of parameterizations and how what the tangent of the parameterization is, and what the dot product is telling us, and how the vector field works, all combined together. Pause for copy. I don't have to read that part of the teleprompter. What I want you to see at this point, is what the integral notation tells us. We're evaluating f dot dr at all the points in the set C. What that means is we're going to have to evaluate the vector field at all the points on the path C. And the dr is just some direction related to the path. That's just going to be the derivative dt. So we're taking our line integral and turning it into this scalar integral. Notice that this is the dot product of two vectors. That's going to give us a scalar function that we integrate with respect to t. One of the things that's not surprising here is that we're integrating over a one-dimensional set. C is a path and it's running through 2 or 3 dimensions or more, who knows. It's a path running through 2 or 3 dimensions, but it's still only forward and backward. It's a one-dimensional path. So we should not be surprised that when we integrate along that path, we get an integral with just one variable. Any questions? Comments? Snide remarks? If you're watching this in the future on YouTube, nobody does, but if you happen to be watching this in the future and you wonder why the fucking lightsaber, it's because it's Halloween today. And that's exciting. If you're from the future and you don't know where my house is, or actually if you're in the present and you know where my house is, you should know that I do hand out full-size bars. Also, if you show up with your kids, the kids get full-size bars, the parents get a beverage. I think I'm kind of very Sith today because I'm wearing all black. And I do have the red crystal in my lightsaber, so I think I'm kind of very Sith today. What's that? I do have my Rebel Alliance pin. Hang on a second. See, so I do have my Rebel Alliance pin going on today, so the pin doesn't quite match. All right. Also, I'm a math teacher, so I mean that's just dark side right there. Actually, on a related note, so the reason we switched to full-size bars, my wife used to do Halloween by like getting a bunch of like the little bite-sized candies and putting them in bags. And she'd make a bunch of these like little Halloween themed bags of candies. And so we were doing that at one point when early on in relationships, like, well, you got to come and do Halloween. I'm like, well, that's fine. I love it. I love Halloween. And so we're packing up all these little bags. I'm like, oh, dude, this is like a lot of work. Why don't we just go get like full-size bars? It's like, oh, that sounds expensive. It's like, oh, nah, you go to Smart and Final or something like that, and you get like a box of full-size bars. It works out to about $1 each. That saves us the time of packing up the things. And I use the argument on her that she always uses on me, like when I was doing my laundry. It's like, oh, just take it to the freaking laundromat. I'm like, oh, yeah, but it's expensive. It's like, well, pay yourself all the time. Pay yourself just minimum wage for the amount of time you spend doing the thing. I'm like, oh, dope. That is a good way to think about it. So I used that. I pulled the Uno reverse and said, look how much time we're spending making these little baggies. And how much time you have to spend because I'm putting too much stuff in the baggies. She's like, okay, well played. So we went to the Smart and Final, got the full-size bars, and we're giving out the full-size bars. It's like one of the first couple of Halloweens at, this is like our second Halloween at the new house. And there's a little kid. The little kid was dressed as Darth Vader. So he reaches in, we hold out the plate of full-size bars, and we're like, oh, grab one, kids. And there's like a little group of 5 kids. And this kid's face just goes like, holy shit. And he looks up at us. He like goes to grab one, and then he pauses and looks up at us. I'm like, oh yeah, kid, grab one. And he like grabs like the full-size Snickers bar, turns around, holds it up to the sky at the top of our porch and says, full-size bars, as if some calling to the rest of the kids in the neighborhood. And he was so excited. So full-size bars from now on. And now we hang out in the driveway, and the kids get full-size bars, parents get a beverage. Adult grape juice. Because we didn't really drink wine, and when you're an adult and you live in a house, like other adults come over, they're like, I don't know, should we bring a bottle of wine? And I go, Leach doesn't really drink wine. Yeah, it's what we're supposed to do, so wine. Anyway, what are we talking about? Line integrals and Sith. I don't have an apprentice, though. Which is the smart play, by the way. If you happen to be a Sith, don't take on an apprentice because they're supposed to like kill you and take over. So just skip that. Don't bother with the apprentice. Just go about your Sith business. Life pro tip. So our integral notation is telling us what we're supposed to do. Here is just thinking about what the vector field is and where we want to evaluate our expression. So important notes. To Wednesday, Thursday, and Friday this week, I will not be on the Zoom. So Wednesday, Thursday, Friday this week, I will not be on Zoom. I'm going to be out of town. Technically, I'm not going to be out of town tomorrow, but I'm going to be at the airport or heading to the airport tomorrow. So I am going to have Professor Quan come in and help you out with some problems. So we have not done any line integral calculations. So you're going to have to sort out how to get through these line integral calculations. So I've got some problems for you to work on over the next 3 days. So if you can make it in, then I would appreciate that you do so. I know in college was like, oh, I'm going to have someone covering for me. They're like, oh, that means class is canceled. It does not. I'm going to have you work on the problems, but instead of me doing problems, you're going to have to work on the problems without me. And then we'll come back on my return. We'll come back and we'll talk about those problems. So I don't know if Professor Quan is going to be able to run Zoom during lectures. If you can't make it, if it's super inconvenient, then totally get it. If you can make it in, we would all really appreciate that. Any questions? Comments? Snide remarks? All right. Oh, math professor could be a Yoda or a Sith Lord. True. Homework you must do. All right, that's going to do it for today. I will see you all on Monday when I get back. Everybody have a good week. Learn how to do line integral calculations. Everybody have a good week, and I'll see you on Monday. Thanks for playing.